Welcome to the next lecture of our course. In this lecture, we will keep focusing more on materials. In the last few lectures, we were looking into material properties. On and off, I have been talking about a polymer, aluminum, I was talking about mild steel, stainless steel. There are a huge variety of material. In the periodic table, you have so many elements. So, there are several combinations with which materials can be developed. Not all combinations work, but with few combinations, for example, zinc copper, they can mix. Aluminium copper, they can mix. Aluminium silicon, they can mix. But in some proportion only, it is not like 50% and 50%. It does not happen like that. So, with the periodic table elements available, assuming that 25% of the material can do a combination with each other to develop material, then you think of it, how many different types of material we will have. And apart from that, you also know the material can be classified as metals, non-metals. And again, under non-metals, you can classify them as ceramic and polymer. Again, in ceramic, you can classify them as oxide and non-oxide ceramics, right. So, you see these classifications are there. All these things are different types of material. Why did so many materials come into existence? To meet out to the application. Today, I need a material which is as light as possible, as stiff as possible, as malleable as possible, as corrosive resistance as possible, and crash resistance as possible. Look at it, we need all combinations. So, putting all these combinations, newer and newer materials come. Saying this, we would try to have this lecture on homogeneous material, isotropic and anisotropic material. The content of this lecture is going to be homogeneous material, isotropic material, anisotropic material. Isotropic, uniform, anisotropic is non-uniform, that is all. Anisotropic material, we will try to see one case study for homogeneous and isotropic material, then case study on anisotropic material. We will have a recap with 2 examples or do it yourself exercise. With that, we will conclude this lecture. Homogeneous material. Homogeneous material are substances that have uniform composition and properties throughout their volume, which is an idealistic case. If you try to reinforce, take concrete, take a cross section of a concrete, you see steel there, you see gravel there, cement there, sand there, mixed together with other composition, mixed together forms a material. So, if you try to take a cross section, it has various things in it. But when we talk about homogeneous material, all should be the same, right. Homogeneous material are substances that have uniform composition and properties throughout their volume. In other words, their mechanical, thermal, chemical composition are consistent and do not vary from one location to the another within the material. Homogeneous material, for idealistic case, yes, it is possible, but in real time when we want to put it into good use, homogeneous material will have different compositions and have different reinforcement. This uniformity means that the material behaves predictable under various conditions. which is very critical for any engineering and scientific application. So, generally what happens, we will try to generalize a given material to homogeneous material, saying that the properties in x direction, y direction, z direction in the center and the edge will be the same. This is used because to find out properties across the cross section is along that varying directions is going to be difficult, right. These materials can be either single phase material such as pure metals and ceramics, or multi-phase material such as alloys and composition, where different phases are uniformly distributed. It can have pure material, but you should understand pure material does not have an engineering application. Okay. Pure material and ceramics or multi-phase material such as alloys and composition, where the different phases are uniformly distributed, falls under homogeneous material. The mathematical representation is P R represents a property. Example, density is defined as rho at a given point R within a material. So, dou P by dou R equal to 0. This implies that P does not change with location R, ensuring uniformity. So, you see here homogeneous element, the pressures are applied and you can see uniform contraction happens under cooling in all the directions. The characteristics of homogeneous material. There are several characteristics. We will start with uniform composition. The material's composition is consistent throughout its volume. Consistent properties will be there. Mechanical, thermal, electrical and chemical properties are uniform across the material. So, it is homogeneous, right. Then single phase or uniform phase distribution either consist of a single phase or a multi-phase uniform distribution. What are multi-phase? Multi-phase materials are alloys. Predictable mechanical properties, it exhibits consistent stress strain behavior, fracture toughness and other mechanical properties, right. So, these are some of the characteristics. If you take an iron, this is a channel, iron channel, which you can see here, it is used in newer construction, prefab constructions, they use it as a beam, and if you see in constructions it is one, or if you want to see in trusses also they use this type of I channel, right. So, you can see here these are the material, and if you further see it down you will see almost the same. Their thermal uniformity is also maintained. Uniform heat conduction and expansion happens. If it is uniform heat conduction and expansion, uniform heat contraction or expansion means that when the object gets solidified, it shrinks uniformly along the x, y and z. So, which is very good. So, we will have a consistency, melt, a solidification happens and it is uniform. Thermal stability is the other thing, resists chemical changes consistently throughout the material. This helps in easy manufacturing. So, manufacturing consistency can be there. It can produce with consistent quality and property. Ease of modeling and simulation, uniform property, simplify mathematical modeling and simulation of material behavior. So, you can see here this is homogeneous material, this is an isotropic material, this is heterogeneous material. Anisotropic material means along one plane you will have different properties when you move in the z direction. So, if you have a cube and then if you cut the cube into several layers along the z direction, you will have non-uniform properties, but you cut a plane, in that plane you will have consistent properties. So, you can have homogeneous, anisotropic, heterogeneous material. So, these are all heterogeneous material. You can see homogeneous material, how uniform properties are there. This is exhaustively used in modeling and simulation. Examples of homogeneous material: pure metals such as gold, known for its excellent thermal conductivity and malleability. Copper, widely used for high electrical and thermal conductivity. But is pure metal used in real time application? No. Pure material is having lot of restrictions in terms of manufacturability. So, what we do is we try to add some elements to it. So, for example, in gold we always add little bit of copper, so that it gives you the strength benefit to it. Same way, alloys, if you see stainless steel is a material wherein which you have a composition of iron, chromium, nickel, etc., depending upon your requirement you start mixing it. Brass is also the same. It has a composition of copper and zinc with consistent mechanical and acoustic properties. So, pure materials also falls under homogeneous. Alloys with uniform properties along the direction falls under homogeneous material. Polymers also fall in the category of homogeneous material. Polymers, for example, polypropylene (PE), used in plastic bags, bottles and pipes, etc., due to its uniform flexibility and strength. Polystyrene, employed in packing and insulation for its consistent thermal and mechanical properties, is an example for homogeneous material. So, you can see here it can be used for pipes, bottles, bags and containers. Ceramics, as I told you, oxide and non-oxide. Oxide ceramics example is alumina. You can also have TiO2, titanium dioxide. You can have silicon dioxide, SiO2. Many examples are there. Alumina, used in cutting tool and electrical insulation for its uniform hardness and thermal stability. Silicon carbide is a non-oxide ceramic. Like this, you can have many things. SiC is one. Then you have tantalum carbide, titanium carbide. You have so many examples of ceramics which are in the non-oxide form. It is very important because you will have to understand the classification. Metals, non-metals. Polymer again can be classified into thermoplast, thermoset, elastomers. And when you talk about ceramics, it can be classified as oxide ceramics and non-oxide ceramics. So, silicon carbide, which finds its application in abrasives and high temperature ceramics for its consistent strength and thermal conductivity. For example, you can see lot of our grinding wheels are made out of SiC. Grinding wheels are, we will see a wheel which rotates at very high speeds, and when the wheel comes in contact with the metal, you will see sparks coming out. So, those operations are called as abrasive grinding operation, where predominantly abrasives are used. Sand is an abrasive. When you fall down, you between a flat surface and you are a soft skin, you have a softer material skin on you. So, when you fall down, you will see lot of times you will be scratches formed in your skin, either in your knee or in your arm. That scratch is created by the abrasive material between the flat surface and the skin. Composites also fall in this category. So, composites, carbon fiber reinforced, used in aerospace and automotive industry for this uniform strength to weight ratio, is also part of homogeneous material. Glass fiber, commonly used in construction and automotive industry for its consistent mechanical property, also falls under homogeneous material. If you see here, it is a composite, so wherein which you have reinforcements done. If you try to take a cross section, you will try to see reinforcements. So, the reinforcements looks like this. You can have a long reinforcement or particulate reinforcement. So, if you see there, it is 0 to 3D, then idealized 0 to 3D composite, particulate unit cell, and then equivalent homogeneous material you can try to have. You have multiple things, but you can try to generalize. So, applications of homogeneous material in aerospace industry, where titanium alloy, aluminum alloy, carbon fiber reinforced polymer are used. So, they are used in making fuselage or aircraft structures, engine components, and spacecraft parts for their consistent mechanical property and lightweight characteristics. Okay. Fuselage is also made out of it. So, you can see here, this is the landing gear. You have a rotor, you have a stator, and then you have a brake disc inside it. So, all these things are homogeneous material. Electronic, for example, silicon, copper, gold. These are some of the examples and application I am taking. Usage, it finds a lot in semiconductor devices, printed circuit boards, and connectors due to their uniform electrical conductivity and reliability. Then construction, you will see steel, concrete, and glass. Usage is structural framework, building facades, and window because of their predictable strength, durability, and aesthetic property. You will have this consistency. If you take in automotive industry, steel alloys, aluminum alloys, and polymers, they use exhaustively. It is used in making chassis, body panels, interior components for their consistent strength, lightweight, and manufacturability. Medical devices, stainless steel use, titanium, and biomedical polymers are used. So, it can be used for making surgical instruments, implants, diagnostic equipments for their biocompatibility, strength, and stability. See, the requirement of automobile and the requirement of medical devices are completely different. Automobile to a large extent is not so stringent as that of medical devices. In medical devices, if the device gets into the body, the material will always be exposed to blood which has a varying pH, right. It can be acidic, it can be basic, when there is a composition change. So, all these, so the material has to be corrosive resistance and the material should not get deformed. So, the requirements for automobile and medical devices are completely different. The requirement for automobile, you can try to increase stiffness, because one way of increasing stiffness is adding material. You can put a thick sheet, because here the mileage matters little bit, but when you go on a plane, the mileage matters very high. So, it has to be stiff, it has to be lightweight. So, people work heavily on material properties. Okay. A simple example is car, of once in 100 kilometers you have a refueling station, but when a plane goes, you will never have a refueling station halfway through. So, it has to be as lightweight, as stiff as possible, as stable as possible. Here in cars, we have now slowly getting into polymers. So, the bumper is made out of polymer. Many of the components are made out of polymer. The battery is now made out of composites, right, and the tire is already a composite material. The white body, lot of parts are made out of composites today. When we talk about electric segment, we always look for high thermal conductivity, low thermal expansion, high stiffness. So, energy sector looks for copper, aluminum, and advanced ceramics. So, here electrical wire, power transmission components, and insulators are having homogeneous property, otherwise it becomes very difficult to control. So, if you see many a times high tension wire which travels between two towers, if the thermal conductivity is very high and expansion is very high, the wire sags. If the wire sags, you have to do one more reinforcement in between. In order to avoid that, what we do is we try to add composition, make it into an alloy such that you maintain stiffness as well as getting electrical conductivity. What are isotropic materials? Isotropic materials are substances that have identical properties in all direction. This means that their mechanical, thermal and other physical properties are uniform and do not vary regardless of the direction of measurement. The term isotropic comes from Greek word iso, means equal. Tropos means way or manner. In this context of material science, isotropic implies that the material's response to external force, temperature change or other environmental factor is the same in every direction. This can be mathematically expressed as E equal to 3K 1 minus 2 mu. This is the way we express the isotropic material. Characteristics of isotropic material is uniform properties. Mechanical, thermal, electrical and other physical properties are consistent in all directions, consistent in stress-strain response, predictable behavior and homogeneous structure. So, these are the characteristics of isotropic material. It will also have equal modulus of elasticity. What is modulus of elasticity? Is E. So, modulus of elasticity is the same in every direction. The property is directional independent. So, the properties such as thermal conductivity, electrical conductivity, coefficient of thermal expansion are independent of direction. The simplicity in modeling is also part of it. It simplifies mathematical modeling and analysis due to uniform property. Metals like steel, aluminum falls under isotropic material. It is widely used in construction industry, automobile and manufacturing industry. Aluminum is commonly used in aerospace, automobile and packaging. When we talk about polymer materials, it talks about polyethylene and polycarbonate. Polyethylene is used for packaging, containers and piping for its uniform flexibility and toughness. Polycarbonate is exhaustively used in electronic, automotive and construction for its consistent impact resistance and transparency. Glasses find an application as soda lime glass and borosilicate glass. When you buy many of the thermal flasks, it is written as borosilicate glasses. In the labs, we see borosilicate glasses. Soda lime glass are used exclusively in windows, bottles and light bulbs for its uniform transparency and durability. Borosilicate glass is used in lab equipments and cookerware. Ceramics are used in electrical insulation, cutting tools and wear resistance components for its uniform hardness and thermal stability. Silicon nitride is used in bearing, turbine blades and other engineering components for its consistent high strength and thermal stability. Composites. Concrete is a composite material. It is utilized in the construction for its uniform compressive strength and durability when properly mixed and cured. Fiber reinforced composite. So, when the fibers are uniformly distributed, these material exhibit an isotropic property ideal for aerospace and automotive application. The application of isotropic is used in steel for building frameworks, bridges and reinforcement bar. Concrete employed in foundation, walls and pavements for its uniform compressive strength. In aerospace industry, aluminum utilizes fuselage, wings, components for its strength to weight ratio and corrosion resistance. Titanium alloys is used in jet engine and airframe components for its uniform mechanical and high strength application. Automotive, we use steel for chassis, body panels and engine components. Polycarbonates are used in headlamp covers, dashboards and interior trims for its consistent impact resistance and transparency. The electronic, we have already discussed. Silicon is used in semiconductor and integrated circuits for uniform electrical property and ability to precisely doped. Copper is used as wiring and PCBs for its consistent electrical conductivity and malleability. The next topic of discussion is going to be anisotropic material. Anisotropic material are substances whose property vary depending on the direction of measurement. Unlike isotropic properties, these exhibit different mechanical, thermal, electrical and optical properties along different axes. This direction dependence arise due to its material's internal structure, such as arrangement of atoms, grains, which lead to varying responses to external forces or environmental condition. This is very important property, please make a note. Anisotropic behavior is significant in many engineering and scientific applications, where materials are subjected to complex loads and stresses. And understanding these directional properties are very crucial for accurate design and analysis. When we do optimization of material, the anisotropic behavior becomes very important for simulation. What are the characteristics? The characteristics are the properties are directional dependent. What are the properties? Mechanical, thermal, electrical, optical, etc., etc. Non-uniform stress strain response. Different stress strain relationship exhibits in different directions, leading to varied deformation and failure modes. Then variable thermal expansion. Different coefficient of thermal expansion in different directions, affecting the dimensional stability of the temperature change. Let us take an example of dosa or chapati. When the chapati is first placed on top of a pan, it has lot of water, so it sticks to the pan, and once the heat is applied and the water is released, the sticking nature is lost and the chapati is released from the pan. So, you see that there is a difference in thermal expansion and one is getting released and the pan is there. So, you have dimensional stability comes into effect. Distinct modulus of elasticity, Young's modulus, shear modulus and Poisson's ratio also varies depending upon the direction of load. Anisotropic conductivity is also very important. So, here electrical and thermal conductivity differs along various axes, impacting heat and electric flow. So, you can see an example here. You have a heat resisted film and then it is placed on a heat resistant mat. Okay. This is a heat resistant film placed on it, and then you have a quartz crystal placed. So, quartz crystal, then heat resistant film, then you have a heat resisted mat. So, below it you have a soldering iron. So, then it is attached to the electric connection. So, here you can see hole through mat and crystal into which the soldering iron is filled or fitted, right. It is basically for joining. So, here you will see different properties are giving along the cross section. So, microstructural anisotropy, internal structure such as grain orientation, crystal lattice arrangement and fiber alignment contributes to anisotropic behavior. Optical anisotropy is also coming up. So, today you have refractive index. So, you have properties where it responds to light in a different way. Refractive index and other optical properties vary with direction affecting the propagation of light. The complex modeling, it requires advanced mathematical modeling and simulation to accurately predict behavior under various loading conditions. The examples of composites are CFRP, carbon fiber reinforced plastics, glass fiber reinforced plastics. So, along the direction, if you make a cross section, the fiber will have a different property, the matrix will have a different property. When you keep laying them layer by layer by layer, and if you cut a cross section, you will have different properties. So, crystalline material, graphite exhibits high electrical conductivity, thermal conductivity along a plane of carbon atoms, but much lower conductivity perpendicular to the plane. You can have quartz. So, quartz is used in electronic oscillators and sensors. Due to its directional piezoelectric property, it is exhaustively used. For example, all the piezo crystals, it will try to measure the force along the x direction, along the y direction, along the z direction. It will be different. So, wood, pine and maple, different mechanical strength and stiffness along the grain versus across the grain, making it anisotropic. Materials like titanium metals and alloys, titanium alloy and rolled steel. So, titanium alloy used in aerospace application, wherein the direction properties can be tailor made along the process or through the process. For example, you have a flat steel sheet, it is rolled between rollers. So, exhibits different properties in rolling direction compared to perpendicular direction used in the structural application. So, if you are rolling it in this direction, the material property in this direction and the material property in this direction will be completely different. Completely different means there will be a difference of 10 to 20% of this thing. Biological material, if you try to take a bone cross section, you will see here densely the bone cells will be adhered or stuck. When we move towards the center, it will be porous. The bones have different mechanical property along different axes due to its composite strength of collagen fibers and mineral matrix. Tendons and ligaments, these exhibits high tensile strength along the fiber direction, but are very weak perpendicular to the fiber. Polymers like Kevlar and PET, which is used for Kevlar and PET, are also examples of anisotropic material used in bulletproof waist and high strength rope with high tensile strength along the fiber axis, but lower strength in other direction. PET, which is polyethylene tetraphthalate, used in packaging, and properties can depend on direction and stretching during the process. Anisotropic finds application in aerospace, carbon fiber reinforced polymers, then titanium alloys, graphite, quartz in electronics, construction where we use glass fiber reinforced plastics, wood, medical devices we have bone implants, tendons and ligament replacement. Optical devices like calcite utilized in polarizing microscopes and other optical instruments due to its directional optical properties. Birefringent crystal used in laser and optical modulators for their ability to manipulate light based on directions. Automotive used advanced composites and aluminum alloys today. Let's take two case studies and understand the homogeneous and isotropic properties. Material aluminum 6061 alloy. This is widely used in applications where there is a combination of mechanical property and good corrosive resistance. This material is homogeneous, meaning it has a uniform composition throughout, and isotropic implying that its properties are same in all direction. What are the properties? Density, Young's modulus, yield strength, ultimate strength, yield strength, ultimate strength. Ultimate will always be larger. Why? You remember we have seen it will go like this. This is ultimate, this is yield, or this will be yield. This will be lower, this will be higher. Stress versus strain. Okay, ultimate. Then thermal conductivity, then electrical conductivity. It finds its application in aerospace components like aircraft frame and parts, automotive engine components and chassis, construction structural beam and column, marine industry shipbuilding components, consumer electronics, casing for devices. The advantages are it has a uniformity, a consistent mechanical property, isotropic, uniform response to stress, corrosion resistance, durable in various environment, machinability, easily shapeable and finishable or easily shaped and finished, weldable, suitable for various fabrication process. Conclusion, its homogeneous and isotropic nature makes it ideal when required uniformity and predictability, making it a versatile choice across various applications. Let's take an example of anisotropic material. Here the material we are considering is CFRP, carbon fiber reinforced plastics. Carbon fiber reinforced plastics are composite materials known for its high strength to weight ratio and directional properties. The material consists of carbon fiber embedded in a polymer matrix, making it anisotropic. The density is 1.6. Tensile strength is 3500 megapascal along the fiber and 230 GPa along the fiber direction. So, the tensile strength is 3500, that is nothing but ultimate, and Young's modulus is 230 GPa. So, if you go back and look into aluminium, look at the Young's modulus is 69 GPa. Here you look at the Young's modulus is 230 GPa. Look at the tensile strength. The tensile strength 310 megapascals. Here it is 3500 megapascals. The thermal conductivity is high along the fiber, low while being perpendicular. So, the applications are, it is used in aerospace, aircraft, spacecraft components. Reason is high strength to weight ratio and tailored stiffness. Automobile, it is high performance car body and components. So, lightweight and strong. Then it is improving fuel efficiency and performance. Sports equipment, tennis racket, bicycle, golf clubs. They are enhanced performance due to their directional strength. Wind turbine blade, the blade construction, high strength and stiffness, reduced weight and improved efficiency along the direction. So, the advantage is it has high strength to weight ratio, directional properties, corrosion resistance and fatigue resistance. What are the challenges? The challenges are the anisotropic material are costly, high manufacturing cost as compared to that of traditional materials. Next is complex manufacturing, specialized technique for fabrication and repair. Brittleness can be more brittle than metal, leading to sudden failure. We are talking about only in the case of glass fiber reinforced. Conclusion, CFRP, high strength to weight ratio and customizable property makes it essential in aerospace, automotive, sports industries despite of its higher cost and complexity. So, the manufacturing processing is difficult. In order to get a good quality output, the cost of the material is high, but looking into the advantage of the properties it displays, people exhaustively use this material. So, to recap, in this lecture, we saw what is the definition of a homogeneous material, why are homogeneous material important in engineering application, what does it mean for a material to be isotropic, two isotropic materials we discussed, why are they considered isotropic? How does an isotropy of the material benefits engineering calculation? Define anisotropic material and provide two examples we saw. What are the key characteristics of anisotropic material? In which engineering field are isotropic material particularly important and why? Compare and contrast homogeneous and heterogeneous material. Why are isotropic material preferred in certain applications? And we saw two case studies to understand the benefit of isotropic and anisotropic material. Okay. So, today do it by yourself experiments. Try to take a stem of a plant. Try to take the cross section of it at various places AA, BB. Try to see that what is the cross section behavior at section AA and section BB. Try to take a cross section at section AA, BB and look at it with your smartphone camera and see what is the cell structure and is there any difference between A and B cross section. Next is you try to take a plastic rod, cut the plastic rod, try to take a thicker plastic rod or your toothbrush, try to cut in two places in the same material, try to see their cross section, see whether you can see any difference in their cross section, right. So, this will try to give you a feel how does the microstructure has an influence in the mechanical property, right. And the last one is you will try to take a sheet of paper, okay. Try to cut the paper or try to take a cloth, try to cut the cloth along this is a handkerchief along this direction AA and along the direction BB. See if there is any difference in your shear load you apply. When you do these three exercises, you will try to understand homogeneous material microstructure, their property response, heterogeneous material, their microstructure and the mechanical property response. These are the references which we have used for this lecture. Thank you very much.